In this video, we're going to talk about radioactive decay. Now, I'm going to build this on some of the things you've seen in the last couple of videos. In the last couple of videos, you've talked about atoms, ions, and isotopes. Atoms come straight off the chart. Ions change their charges, and isotopes are heavier or lighter versions of an element. Just as a reminder, okay, this is what you're going to see in a straight off the periodic table are going to be atoms, just the way they sit. Ions are going to be positive or negatively charged. So basically this happens by changing electrons. And then isotopes are going to be heavier or lighter versions of an atom due to changing neutrons. And so what we're going to focus on here is radioactive decay. Now it's going to fall sort of under this column of isotopes. Now, very important that you write this down. Star. Not all isotopes are radioactive. Not all isotopes are radioactive, but some of them are. And we've learned how to use them for some really, really cool things in medicine, and we've learned how to use them for alternate sources of energy, like in nuclear power plants, and then we've learned how to use them for bad things, like putting them on the end of a bomb, and when they hit the ground, we can actually cause destruction. So we're going to talk about what is radioactive decay and how does it happen. Alright, so I'm going to erase this real quick. Now I'm going to move the camera in a little different way for this lesson, and let's see how this turns out. Now the picture is going to be sideways just a little bit, but you will notice right here that I have a stack of wooden blocks. These are the little wooden blocks like you would have used as a little kid. You'd stack up, they have letters on them, that kind of thing. And trying to explain what radioactivity is, and move the camera just a little bit more. I want to use this example. So you'll notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blocks. They look pretty steady. Now, could I take these 11 blocks and stack them all the way to the ceiling without them falling? Well, if I had a bigger base area, I might. But in a single stack like this, it's not going to happen. Now, let me show you what's going to happen if I add one more. See if I can be steady here. See that thing starting to waver a lot? See it starting to shake? Okay? This is what happens when something is radioactive. Okay? It's too big for itself. Okay? So I want to use this scenario one more time. Let's see what happens if I add another block. Oh, it really starts to shake. It's really, really, really starting to shake. I'll move the camera so you can see a little bit more. And I'll try one more. You can tell that it would all fall down. Now, let's take that scenario and apply it to radioactivity. Now, let me adjust my camera real quick for you. Let's talk about radioactivity. What is radioactivity and how does it actually work? Now, I'm sorry the picture was a little bit sideways, but I think you can really get the idea of what's going on. It takes me a second to adjust my camera. So let's talk about radioactivity. Alright? Let's use this example. Uranium-238 is a very, very common isotope of uranium. Now let me explain real quick. If you look at uranium-238 is the actual mass right off the chart. And there are different varieties. But it happens to be radioactive. Now, how do I know that? Well, before we get too far, let me go ahead and put a star in your notes real quick. All elements above 84 polonium are radioactive. All elements above 84 and above. Maybe I should rewrite that. all elements 84 and above, which is polonium, are radioactive. Okay, let me fix that and say that a little better. All elements, so element 84, which is polonium, and above are all radioactive. All of them. Now, why is that true? Well, it goes right back to that block stack that I just had. They're just too big for themselves. If you want to imagine for a second that this is a nucleus of an atom, and there are protons, neutrons, electrons, and all I have is this little kid's toy set, and I have all these protons, neutrons, electrons, and I have them sort of stacked together to try to sort of make them together. And then you would have the electrons spinning around the outside in these different rings. Okay? This nucleus gets too large. When you get 84 and above, for some reason it's too large and it can't stay together. Just like that stack of blocks that I was just using. As I started adding them and getting them higher and higher and higher, there was a point at which they fell apart. And that's what happens in radioactive decay. Now notice the word decay. When something decays, it falls apart. And it's going to fall apart. Now, uranium is element number 92 on the periodic table. 92 right there. So it's above 84, so it's automatically radioactive. Now what's going to happen is this. There are three ways, or three forms, of radioactive decay. Three forms of radioactive decay. My pen's dying, so I'm going to switch. The first one we're going to talk about, there's its symbol, called alpha decay. Alpha decay. And we're going to talk about that one first. We'll do them one at a time. All right? Alpha decay. Here's what happens. Let's go back to this little imaginative one that we were using. And let's say that this is uranium. It has lots and lots of parts. As a matter of fact, it has 92 protons, 92 electrons. We learned this in one of the last videos. And 146 neutrons. Now, how did I do that so fast? Well, protons plus neutrons have to equal 238. Okay, and so 92 and 146 is 238. So that's its weight. Now remember, when it's written like this, it can be written as an isotope. And so I have a really, really big nucleus. Now I don't have all 238 parts, but we'll just pretend here for a minute. What happens is it's too big, and so it's going to go through radioactive decay. The first type is what is called an alpha decay. Here's what an alpha decay is. It is represented with a 4-2 helium. That's how it's represented. So it looks maybe something like that. Okay? So what does that mean? Well, it's got 2 protons. There they are. And 2 neutrons. And it's a group. So there's 4 total parts. 2 of them are protons. Now, why do they call it a helium? Well, if you look on the periodic table, 2 protons on the periodic table is helium. And so what's going to happen is, let's go ahead and put that in the nucleus just like that for a second, is if I had that big stack of blocks again, when it started shaking, if I pulled a block off the top, it would immediately start, it wouldn't fall anymore. As I take more and more blocks off the stack, it gets more and more steady, and that's what the atom's going to try to do. So what's going to happen is this molecule, this nucleus is going to, and let me draw the electrons like this. So we'd have all these rings of electrons, and it'll go through alpha decay, and here's what happens. This flies off. Well, when that flies off, there is a change that takes place, and it's simple math. U238, 92, and the math works like this. I just had a 4-2 helium. I'll just draw it like this so we understand. It flies off. Now, do I still have 238 parts in there? No. Part of it's gone. So if I do simple math, 238, I lost 4. That's a 234. And 90 minus 2 is 90. Now, I can always check my math. 234 plus 4 is 238, and 90 plus 2 is 92. What happens if I change the protons? Is it uranium anymore? Well, let's look at the chart. If I look at element, I was at uranium, which was 92. Now I'm going to move to number 90, which is TH, thorium. So it actually changed elements. It's not the same element anymore. So when this thing flies off and goes away, it now is a new element. Now, is that still radioactive? Now remember, look at the star you wrote in your notes. 84 and above are all radioactive. Is that 84 and above? Absolutely it is. It's a 90. So somewhere down the road, it can do it again. So that 234-90 thorium can go through a 4-2 helium, which is an alpha decay. Well, what's left? Well, if 234 loses 4, now I draw this arrow just to help me remember, it just flies off and it just goes away. I have 230 parts and 88. Well, all it is using the periodic table again. 88 is Ra right there. And so it went through an alpha decay. So basically what's going to happen is another one of these particles flies off and it's slowly getting smaller. You'll notice we started at 92 protons, then we fell to 90 and 88. So it's dropping 2 elements every time. Is this one still radioactive right here? Sure it is. It's above 84, and it can continue to do that. This is called alpha decay. Now, it doesn't just happen for uranium. Let me erase and show you another one. So instead of uranium, let's take something off the periodic table. Let's take 245-96 curium. All right. Mathematically on paper, when it goes through alpha decay, you just have to remember this part right here. It's going to fly off. What's left? Well, 241 plus 4 is 245, and that's a 94. And so when I look on the chart, 94 is plutonium. So it's simple math. You should always be able to add back and get your answer. 94 and 2 is 96. 241 and 4 is 245. So alpha decay is pretty easy. It's just this particle that's flying off. Now remember, why would it want to do that? It's trying to get the nucleus small so that it'll be steady again. It's just too big for itself. And so it's going to try to lose particles. Now that's